So we left it with um, a lot of observational, seemingly overwhelmingly observational evidence and a complete theoretical explanation of light as a wave. But I mentioned that there were a few apparently small problems, ones nobody really thought would upset the whole picture of light. But here they were. The first one is what's called the black body problem. Black body radiation has to do with how heated objects give off their radiation. And without getting into the details of the problem, the issue was that if you predict from light as a wave how it should behave, the Rayleigh-Jeans law actually predicts what light as a wave should do. So if light is a wave, this curve here describes what we should observe when an object is releasing light. The reality, though, is this, the observed spectrum, that light as it's emitted actually rises to some peak at a particular wavelength and then descends. It forms what's called a bell curve because it's shaped like a bell. That's very different from what the wave theory of light predicted. So the first problem was that the wavelengths of electromagnetic radiation simply were not observed to be emitted by heating objects as was predicted by the wave theory of light. The second problem is something that we've already met. The spectral lines that we observe as light is emitted or absorbed by gases. Because if energy is a wave, and waves are continuous, they're spread out over space, if energy is continuous, then the gas atoms should emit any and all wavelengths, and they should absorb any and all wavelengths, but they don't. The spectral lines that we've talked about previously are very, very specific wavelengths of light that are emitted. This shouldn't happen if light is a wave. The third problem is something called the photoelectric effect. Now, you may never have heard of the photoelectric effect, but you're familiar with its applications. The photoelectric effect is simply a name for the observation that when light of a sufficient energy strikes a metal, electrons are actually ejected. And you probably know that electricity is the movement of electrons. So we can actually use the photoelectric effect to generate electricity. And we do in many applications. This little plate here on a solar powered calculator is a little piece of metal, and the light that hits it ejects electrons and generates the electricity for the calculator. On a large scale, this is what we do with solar panels. Now, the wave nature of light has no problem explaining qualitatively the photoelectric effect. Waves can knock particles out of the way. But the problem was that when the photoelectric effect was studied quantitatively, how many electrons were ejected, depending on what intensity of light, what energy they came out with, the numbers simply didn't match the predictions if light really is a wave. So there were these three problems. The way heated matter emits light didn't match what was predicted by the wave theory of light. The existence of spectral lines didn't match the prediction of the wave theory of light, and the details of the photoelectric effect didn't match the wave theory of light. How those were dealt with, we'll look at in the next video.